the mid-segments of a triangle. Each side has a midpoint. We've already introduced in a previous video that if we connect a vertex to a midpoint, we have just drawn a median. Now, if we draw a line or a segment that connects midpoint to midpoint, we have just drawn a mid-segment. And there are 3 mid-segments, and there's some special properties or relationships the mid-segments have to some of the sides. So to derive those properties, let's assign some coordinates to our vertices. Well, we know that these are supposed to represent midpoints, these points I'm connecting. So if I want to find the midpoint, we'll assign some more capital letters for, if we want the midpoint of AB, again, we just average the x's and average the y's. So this location, we'll call this point D, is going to be A plus C over 2 and B plus D over 2. And we could repeat this process for A plus E over 2 and B plus F over 2. And then this one, which we'll call F, will be C plus E over 2 and D plus F over 2. So to find the location of those midpoints, we're just going to average the x and y coordinates of the vertices that form that side. And now, what we're going to look at is, it looks in this diagram like the mid-segment I've drawn should run parallel to one of the sides. So mid-segment DF should run parallel to AC, and we could do that by calculating slope. So if the slopes are the same, they'll be parallel. So let's do that. So let's say the slope of AC, so that bottom side, will be change in y, so F minus B over change in x, which is A minus E. The slope of DF, let's see if that ends up being the same. So we're going to have to do change in y, which is F plus D over 2 minus B plus D over 2 all over the change in x. So C plus E over 2 minus A plus C over 2. If we simplify this, what we're going to get up top, this negative would distribute in. So up top, and they have common denominators, so we can put it all over 1. We're going to have F plus D minus B minus D all over 2. And on the bottom, we're going to have C plus E minus A minus C all over 2. So we have this complex fraction, but first let's simplify. These D's cancel, and so do these C's. So here's what we have now. F minus B over 2 and E minus A over 2. Oh, I've made a simple mistake on AC because we went F minus B. I should have done E minus A, not A minus E. So stay consistent in which path you go. So we have this complex fraction. So dividing by this bottom piece is the same as multiplying by that reciprocal. So we can say F minus B over 2 times 2 over E minus A. That will reveal our slope of DF. And you can see that those 2's will cancel and we'll get F minus B over E minus A. And would you notice that they have the same slopes for whatever the values of A, B, F, and E are. Therefore, we have just proven, by just assigning abstract representations for our 3 coordinates, that this mid-segment here runs parallel to that side. And that's true for all of them. So this mid-segment will run parallel to this, and you could work through the math on that. And this mid-segment will run parallel to this side. And the reason why that's important is because we know when we have parallel lines, we have these angle relationships that are formed. For instance, if DF and AC, as we were just proving, are parallel, we can think of AB, that side off on the left, as a transversal, And therefore, this angle and this angle are congruent because they're corresponding. And we can draw that corresponding relationships in many other locations, like here, or here with the original one. But also, we can see that there would be like alternate interior angles that pop up. So if we look at FDE, this angle in here, that would be congruent to AED, this angle in here, because they're alternate interior. So we see things like that are popping up, and we could even say that this angle C that we wrote should be supplementary to this angle in here, because these are same side interior. So a bunch of angle relationships pop up from these mid segments and the fact that they run parallel to one of the sides. Now, the other thing that's true about the mid segment is the length in relation to the side it runs parallel to. So let's draw our so the length of DE in relation to AC. What we could do is actually calculate the distances through the distance formula if we want. So that involves a little bit. Let's do it. So let's call AC, we'll call it x1, y1. And this x3, y3. And this x2, y2. Then over here for D, we're going to have the midpoint of that. So it's going to be x1 plus y, or x2, sorry, over 2, and y1 plus y2 over 2. And then here we're going to have x2 plus x3 over 2, and then y2 plus y3 over 2. So again, we're just averaging the x's and y's for the coordinates of our vertices to find the midpoints, which are labeled as D, E, and F. Now, we want to find the length of DE and the length of AC and see if there's a relationship between them. So the length of AC, we can use distance formula. So say AC is equal to the square root of the sum of the x coordinate squared, or sorry, the difference of the x coordinate squared. So it's going to be x1 minus x3 squared plus the difference of the y coordinate squared. And we'll just leave it like that for now. And now for DE, that distance is going to be the change in the x's squared. So it's going to be x1 plus x2 over 2 minus x2 plus x3 over 2, all of this squared, plus the difference in the y's. So it's going to be y1 plus y2 over 2 minus y2 plus y3 over 2 squared. So this looks like a mess, but if we clean this up, let's see if there's some relationship. So we can work with this parenthesis first, and then we'll see what results from that. So if we distribute that negative, you'll notice that the x2's cancel. And what we're going to have is x1 plus, or sorry, minus x3 over 2 squared. Plus, when this negative distributes in here, you'll notice that the y2's will cancel. So we'll have, and we're going to combine them because they have common denominators. So we're going to have y1 plus y3, or sorry, minus y3 because the negative distributes, over 2 squared, square root of that. Okay, so you may have noticed I put parentheses around the second piece when I was subtracting it because we want to subtract that entire quantity so that I remember to distribute the negative. That's why this is in parentheses and this is in parentheses, because if I did not have it there, I would forget to distribute that negative into the numerator, which is necessary to illustrate what's actually happening. Now, each of these things gets squared. So let's clean this up further. And we're going to notice there's a nice relationship that happens. So when I square this first, we're just going to write square root, and we're going to leave it as x1 minus x3 squared, but when I square the denominator, we're going to get 4. So now we square that whole thing, plus y1 minus y3 squared over 4. Now these both have common denominators, so we can put them together, and we're going to get square root of x1 minus x3 squared plus y1 minus y3 squared all over 4. Square root properties tell me I can split this into x1 minus x3 squared plus y1 minus y3 squared all over the square root of 4. And the square root of 4 is 2. And if I bring that 2 to the front, dividing by 2 is the same thing as multiplying by 1/2. So what we can say is 1/2 the square root of x1 minus x3 squared plus y1 minus y3 squared. Now what's important of what we just derived, going back to the top here, is that AC, that bottom side was this. And that is the exact square root that popped up when we simplified all that work at the bottom. The only thing is that there's a 1/2 in the front. So this piece here, that I'm boxing off, maybe I should do it in a different color, is the length of AC from what we first found. So this here is AC. So when we found the distance between D and E, we found out that that is 1/2 times the distance from AC. And we could repeat this process for the other midsegments, but the conclusion that we can draw is that the midsegment is half the length of the side it runs parallel to. So let's draw those conclusions to finish off this video. We're going to say DE is equal to 1/2 the side it runs parallel to AC. The same could be true about FD being 1/2 of BC. And also FE being 1/2 of AB. And we can flip all of these to show that the side that forms the original triangle should be 2 times the length of its midsegment that runs parallel to it. So I could also say that AC should be 2 times DE, or that BC should be 2 times FD, or that AB should be 2 times FE. So we were able to use distance formula by assigning some just abstract representations for the locations of our vertices, and then able to represent our midpoints. Then using distance formula and some algebra simplifications, we were able to find that the midsegment should be half the length of the side it runs parallel to, or the side of the triangle should be 2 times the length of the midsegment that runs parallel to it. So there's the conclusion of the video for length relationships in midsegments and the angle relationships that are formed because of the fact that they are parallel.